In this chapter, we're going to look at one-dimensional motion. Motion means, as you know, change in location with time, and one-dimensional motion means motion in a straight line. So in this chapter, we're going to look at particles moving in a straight line. So one-dimensional motion is motion in a straight line. Now, to discuss motion, first we're going to need to define motion variables. So in this section, we're going to look at motion variables, the variables used to describe motion. Okay, since motion is changing location with time, the first physical quantity we need to define is position. We're going to use x if the motion is horizontal and y if the motion is vertical. So you can say position is a physical quantity used to specify location. Okay, so position specifies location. This is a physical quantity used to specify location. Now, position requires a reference point or origin. Requires a reference point or origin. Okay, suppose if I ask you where is this point located, you have to describe it in relation to some reference. For example, you can say this much from here. Okay, so the value of position depends on the choice of origin. Position does not have a unique value. Its value depends on where you put your origin. So position does not have a unique value. What that means is depends on reference point. Depends on origin, on choice of origin. Okay. For example, consider the following number line. Let's say these are separated by a centimeter. Let's say B, C, D, E, F, maybe G, and so on. Now, suppose I want to determine the location of point D. Okay. Now, if origin is at A, the position will be 3 units to the right. Position to the right is positive, position to the left is negative. So if my origin is over here, that's if I put my 0 over here, then the position of xd will be 1, 2, 3. Okay? How about if origin is at E? If origin is at E, the value changes. Okay? If I put my origin over here, then it is 1 to the left, which means xd equals -1. Okay, so position does not have a unique value. Its value depends on where you put the origin. And of course, the unit of measurement for position is meters. Next, we're going to look at displacement. Displacement is simply change in position. This is change in position. We're going to use delta x for this one. So you can say displacement delta x is simply final location minus initial location. Okay. So obviously the unit of displacement is meters because the unit of position is meter. Now, position does not depend on reference. Displacement does not depend on origin or reference point. Does not depend on the choice of origin. Now, if a particle is displaced to the right, displacement will be positive because the final is bigger than the initial. But if a particle is displaced to the left, then displacement will be negative because the final point is smaller than the initial point. So displacement is positive if displaced to the right, and it's negative if the particle is displaced to the left. For example, let's say we have the number line over here. Let's say these are the points C, D, let's say E over here. Now, let's say particle displaced from B to D. Okay, so it's displaced 2 units to the right, so displacement is going to be 2. Or you can say displacement, in this case, the final is D, xd minus xb. Okay, if origin is fixed at A over here, okay, then the position of D is 1, 2, 3, okay, 3 centimeters, and the position of B is 1 centimeters, so you get 2 centimeters. That is if origin is located point A. You can use any other origin and still will be 2 centimeters. It just means it's displaced by 2 units to the right, irrespective of where you put the origin. Okay, for example, you put your origin at E, the final point would be -1, and the initial point would be 1, 2, 3, -3. Okay, so -1 minus -3 will still be 2 centimeters. So displacement does not depend on the choice of origin. And displacement to the right is positive, displacement to the left is negative. Now let's consider average velocity. Average velocity. Average velocity is defined to be displacement per a unit time. Displacement per a unit time. A unit time. Mathematically, you can write as, we're going to use V bar to represent velocity. So it is displacement divided by time taken. Okay, or you can say x final minus x initial divided by t final minus t initial. We can usually assume the initial time to be 0, so we can simply say it's xf minus xi divided by the time taken. So as you can see from this equation, the unit of velocity is the unit of position, which is meter, divided by the unit of time, which is second. Okay, now time is always positive, so the sign of average velocity is the sign of displacement. So velocity to the right is taken to be positive, while velocity to the left is taken to be negative. Okay, if a particle is displaced to the right, this expression will be positive, so the velocity will be positive. If a particle is displaced to the left, then this expression will be negative and the velocity will be negative. So velocity to the right is positive and velocity to the left is negative. So you can say V average is positive if motion to the right, negative if moving to the left. If moving to the left. Okay, and then let's look at instantaneous velocity. Instantaneous velocity, this is velocity at a given instant of time. It's the kind of velocity you read in your odometer. Okay, so it is velocity at a given instant of time, or you can say it's average velocity evaluated at a very, very small interval of time. So let's use that definition. This is basically average velocity evaluated at a very, very small interval of time. Small interval of time. So you start with the definition of average velocity, which is delta x divided by delta t, displacement divided by time. Now if you push this delta t, time taken, to 0, it becomes instantaneous velocity. I know in this course we're not supposed to use calculus, but in the language of calculus, this can be written as This is the limiting value of this expression as delta t approaches 0. This is the definition of velocity. Okay, it is average velocity evaluated at a very, very small interval of time. And then we have average acceleration. Well, first let's look at the unit of this one. Unit is the unit of displacement, meter, divided by second, just like average velocity. Okay, let's look at average acceleration. Average acceleration. Acceleration or average acceleration is defined to be change in velocity per a unit time. In other words, is the rate of change of velocity. So average acceleration, we're going to use a bar, is defined to be change in velocity per a unit time. So mathematically we can say average acceleration is change in velocity divided by change in time. Okay, or you can say this is v final minus v initial divided by t final minus t initial. Okay, so we can usually set the initial time as 0, so we can just say this is change in velocity divided by time. Okay, now let's look at the unit. The unit of acceleration would be the unit of velocity, which is meters per second, divided by the unit of time, which is meters per second square. So the unit of acceleration is meters per second square. Now let's look at the sign of average acceleration. If the final velocity is bigger than the initial velocity, okay, this will be positive. Time is this will be positive. Time is always positive, so the average acceleration will be positive. But if the velocity is decreasing, you see the final velocity is smaller than the initial velocity, so the acceleration will be negative. So acceleration is positive if the velocity is increasing, and negative if the velocity is decreasing. Now let's look at instantaneous acceleration. Instantaneous acceleration. This is acceleration at a given instant of time, or we can say it is average acceleration evaluated at a very, very small interval of time. So let's use this definition. This is average acceleration evaluated at a very, very small interval of time. So we can start from the average, which is delta v divided by delta t. If you take the limit of this as delta t approaches 0, then you get instantaneous acceleration. Okay, so these are the variables we need to discuss: motion, position, displacement, velocity, and acceleration. Now let's look at some examples. Let's say we have the following number line. Let's say each unit is centimeters. So you've got point A over here, point B, point C, point D, point E, F, G, and so on. Now, assuming the origin is at x equals c, okay, find the position of let's say A, let's say E, okay. So xe You see, now our origin is C, so E is 2 centimeters to the right. Okay, so the position will be 2 centimeters. All right, how about the position of point A? Okay, XA. Now with respect to point C, our origin over here, it's 2 to the left, so XA is -2 centimeters. Okay, so remember, position depends on the choice of reference point. If you put the origin, for example, at C, if you put the origin at point A, E would be 1, 2, 3, 4, and A would be 0. Okay, they'll be different numbers. All right. Number 2, let's say a particle is displaced from let's say D to A. Okay, now let's assume the origin is placed at point A. Okay, so we have delta x is, the final is A, XA minus XD. Okay, so it's being displaced from D to A. It's going from here, it's going this way. Okay, so obviously it's being displaced by 3 units to the left. Okay, that'll be -3 centimeters. But if you want to be technical about it, okay, let's put our origin at A. If the origin is at A, then the location of, if origin is at A, so obviously XA equals 0 and XD equals 3 centimeters. 3 centimeters. Okay, so we'll have delta x equals XA 0 minus 3, which is -3 centimeters. It basically means it's displaced to the left by 3 centimeters. So it doesn't matter what reference point you use, the displacement would always be the same. Okay, now let's compare distance and displacement. Distance and displacement are very, very different quantities. Okay, let's say a particle is displaced from A to E and then back to, let's say, to B. Okay, so first let's calculate displacement. Displacement in this case would be x final minus x initial. All right, now the final is B, x final is B, and x initial is A. So the displacement is simply the position of point B minus the position of point A. All right, that is xB minus xa. So it's being displaced from A to B. So you see, it's displaced only by 1 unit. In the case of displacement, you just look at the initial and final point. It started from here, we went all the way to E, and then came back to this point, right? We went all the way over here, and then came back to B. Okay, so this is a displacement, but distance is this entire distance over here, from here to here. Okay, so they're very different quantities. So this would be 1 centimeter. It's moved by 1 unit to the right, which is positive. But for distance, you see the distance, this whole thing. You went 1, 2, 3, 4 in this direction, and then came back 1, 2, 3. So it's going to be 4 plus 3 or 7 centimeters. So distance would be 7 centimeters. That is 4 this way, 3 back, plus 3, 7 centimeters. So you see, displacement and distance are very, very different quantities. In the case of displacement, all you look at is the final point, initial point, but distance is the whole distance covered. So it's very important that you know the difference between distance and displacement. In physics, equations are usually written in terms of delta x. Okay, so it's very important you know the difference between distance and displacement. Actually, let's say it came from A to E and then back to A, from A to E and back to A, it will be 0 because the final initial are the same. Okay. Now let's say a particle is displaced from, let's say, from point E to B in 10 seconds. In 10 seconds. So let's calculate average velocity, or V bar. V bar is delta x divided by delta t, or x final minus x initial divided by time taken. Okay, so the initial is the position of E. So the position of E, if you put your origin at point A, the position of E will be 1, 2, 3, 4. Okay, so xe would be 4. This would be 4 centimeters, and x final is the position of point B with respect to A is 1 centimeters. So and of course time taken is 10 seconds according to the problem. So the average velocity, which is x final minus x initial divided by t, or xe minus xb, which is 4 minus 1 divided by 10, would be that would be 1 minus 4, would be negative 3 over 10, or negative 0.3 centimeter per second. Okay, it's negative because it's being displaced to the left. Now again, let's see the difference between average velocity and average speed. Okay, they're very different concepts because speed is defined in terms of distance, but velocity is defined in terms of displacement. Okay, speed is expressed in terms of distance, while velocity is expressed in terms of velocity. For example, let's say we have this number line over here, 0, 1, 2, 3, 4, 5, let's say. So let's say a particle goes from here to here, back to this point over here. Okay, so for displacement, this is a displacement, this is delta x. Okay, no, I'm sorry, this is the final point over here. This is the initial, this is the final point. This is displacement, which is negative 1. Okay, so delta x in this case is 1 to the left, which is negative 1 centimeters, and time taken, let's say this trip took 10 seconds, okay, to go from here to here. All right, so the average velocity would be delta x divided by time, will be negative 1 over 10, or negative 0.1 centimeter per second. But average speed is defined to be distance divided by time. Okay, now the distance is this whole thing. You got 1, 3, 4. Well, we got 3 units in this direction, and then 4 units in this direction. So total distance traveled is 7. You see 1, 2, 3, and then 4, 5, 6, 7. All right. So average velocity would be 7 divided by 10, or 0.7 centimeter per second. So you see that average speed and average velocity are very different quantities, because average velocity is defined in terms of displacement, while average speed is defined in terms of distance. Because of that, speed and velocity are very different quantities. Now let's look at acceleration. Let's say the velocity of a particle, let's say change it from, let's say 4 meters per second to 1 meters per second, let's say in 10 seconds. Okay, the question is calculate acceleration. Calculate acceleration. Acceleration, of course, average acceleration. Okay. Now the definition of average acceleration is final velocity minus initial velocity divided by time. So we're told it started from 4 meters per second, that's initial velocity, 4 meters per second, and then end up with a speed of 1 meters per second, or velocity 1 meters per second. So that's final equals 1 meters per second, and we're told the time taken is 10 seconds. Okay, so the average acceleration would be v final 1 meters per second minus initial minus 4 divided by 10. That is negative 3 over 10, or negative 0.3 meters per second squared. Okay, so average acceleration is simply change in velocity divided by time taken. In this section, we're going to look at motion graphs. First, we're going to look at the graph of position versus time. The graph of position versus time. So let's put the position on the vertical axis and time on the horizontal axis like this. So this is what you call motion graph. So let's say the graph of the position versus time for a certain particle looks something like this. Okay, and let's say we want to find the average velocity between these 2 points. All right, so let's say this is initial time over here, this is final time over here, this is going to be initial position, and this is going to be final position. Okay, now let's look at the definition of average velocity. Average velocity by definition is x final minus x initial divided by t final minus t initial. Now look at the graph. This interval over here is t final minus t initial, and this interval over here is x final minus x initial. Now this is vertical change, this is horizontal change. The ratio between the vertical change and the horizontal change is the slope of the straight line joining these 2 points over here. Okay, so you can say that average velocity can be obtained from a graph of position versus time at the slope of the line joining the 2 events. Okay, so by definition, average velocity is change in position divided by change in time. So if you look at the graph, the ratio between change in position and change in time is vertical increase divided by horizontal change over here, which is defined to be slope in math. Okay, so you can say that average velocity can be obtained from a graph of position versus time at the slope of the line joining the 2 events. So the conclusion is average velocity can be obtained from the graph of position versus time at the slope of the line joining the two eventus. The line joining the two eventus. Alright, the two eventus. Alright, now let's look at instantaneous velocity. Instantaneous velocity, if you remember, is average velocity measured a very, very small interval of time. Okay, so if you keep pushing this final time towards the initial time, you see, if you're over here of this line over here, if you get closer of this line, eventually as the difference tf minus t approach 0, is going to be the slope of the line touching the point, touching the curve at one point, which is the tangent line. So the conclusion is instantaneous velocity can be obtained from the graph of position versus time at the slope of the line tangent the curve at the given point. Okay, to find instantaneous velocity from a graph of position versus time at a certain point, you simply find the tangent line, which is the line touching the graph at one point, and you measure the slope of that line. That'll give instantaneous velocity. So the conclusion is instantaneous velocity is the limiting value of this one. You take delta x over delta t, and then you push delta t to 0. Okay, graphically, instantaneous velocity can be obtained as the slope of the line tangent to the curve, at the given point, So average velocity is the slope of the line joining the two eventus, but for instantaneous velocity, the two times have to be very, very close to each other. That is, as the difference time approaches 0, the line basically becomes a line touching the graph at one point, which is the tangent line. So instantaneous velocity can be obtained from the graph of position versus time as the slope of the line tangents the curve at the given point. Now let's look at the graph of velocity versus time. The graph of velocity versus time. Let's put the velocity on the vertical axis. This will be the velocity, and this will be the time. Okay, suppose the curve of velocity versus time looks something like this. Okay, and we're trying to find the average acceleration in these 2 points. Okay, so you've got this is the initial time, this one over here is the final time, and then this would be the initial velocity, and this would be the final velocity. Okay, so by definition, average acceleration is v final minus t initial divided by t final, v initial, and then t final minus t initial. Okay, now let's look at these differences. T final minus t initial is this interval over here. Okay, this over here, and v final minus v initial is this interval over here, vf minus vi. Okay, so according to this graph, average acceleration is the ratio between the vertical change over here and the horizontal change over here. But as you know, the ratio between vertical change and horizontal change is the slope of the line joining the two events. Okay, so you can say that average acceleration can be obtained from a graph of velocity versus time at the slope of the line joining the two events. Okay, so the conclusion is average acceleration can be obtained from the graph of velocity versus time, as the slope of the line joining the two events, Okay, so to get average acceleration from a graph velocity versus time, all it is, you connect these 2 points, the straight line over here, and the slope of that line gives you the average of the acceleration in this time interval. Okay, next let's look at instantaneous acceleration. Instantaneous acceleration is you take the ratio between delta V and delta t, which is average acceleration, and then you take the limit of this as delta t approaches 0. That gives you instantaneous acceleration. In other words, you bring these two times closer and closer to each other, so the difference is close to 0. Let's keep pushing this towards ti. Okay, so you get this line, when you put over here with this line, so eventually as delta t at this time difference approaches 0, this line would be a line touching the curve at 1 point, okay, which is the tangent line. So we can say that instantaneous acceleration can be obtained from the graph of velocity versus time at the slope of the line tangent to the curve. So you can say that instantaneous acceleration can be obtained as the slope of the line tangent to the curve at the given point, Okay, so to get instantaneous acceleration from a graph of velocity versus time, all it is, you draw the tangent line at the given point, which is a line touching the curve at 1 point, then the slope of that line would give you instantaneous acceleration. And if you want to find the average acceleration in a certain time interval, all it is, you connect those 2 points, the initial point and the final point in the velocity versus time curve, and then you find the slope of that line. That'll give you the average acceleration in that interval. Okay, next let's see how we can get displacement from a graph of velocity versus time. Okay, let's look at displacement. Let's start from an easier situation. Let's say the velocity is a constant like this. Okay, this is the velocity, this time over here. All right, but we know that displacement delta x, well, if this is a constant, then instantaneous and average velocity will be the same. So you got delta x equals average velocity times time, because average velocity is displacement divided by time. Okay, now this is time, this over here is the average velocity v bar. Okay, if you take the product of this, which is average velocity, and this one the time, you get the area of this curve over here. Okay, that's the area of the rectangle. If you take the product of the velocity and the time, you get the area of this rectangle. So even though this is for the case where the velocity is constant, this applies for any kind of a curve. If you have a graph that looks something like this, if this velocity, this is time, then the displacement will simply be the graph between the graph of velocity versus time and the time axis. Okay, so we can say that displacement can be obtained from the graph of velocity versus time as the area enclosed between the velocity versus time curve, between the velocity versus time curve and the time axis So you see this is the velocity versus time curve, and you take the area enclosed between this axis, the time axis, and this curve over here. This area over here is equal to the displacement. Okay, now you see in this case positive velocity means it's moving to the right. Okay, so if it's moving to the right, displacement is positive. Okay, how about if you have something like this? Let's say the curve is like this. Okay, so this means the velocity is negative. Negative velocity means the particle is moving to the left. So that tells you this area should be negative. Okay, it's moving to the left, the displacement will be negative. So areas above the time axis are taken to be positive, while areas below the time axis are taken to be negative, because if the area is below the time axis, it means the velocity is negative, and that also makes the displacement negative because it's moving to the left. Okay, so areas above the time axis are taken to be positive, while areas below the time axis are taken to be negative. All right, now we're going to look at some examples. Let's have a graph. Let's say this is our graph. Let's say it's 1, 2, 3, 4, 5, and so on. And let's say it's 1, 2, 3, 4, maybe -1, -2, -3, -4. Okay, suppose we have the following graph. Suppose it goes well, let's say this is 1 over here, this one 2. Anyway, let's say this is 3 over here. So let's say it goes over here like this, and then it starts decreasing like this, and then it goes like this, let's say. So this one over here is 2, this one is 3, and this point over here is also 3. All right, so now let's ask some questions. Number 1, so this is the position and this is time over here. Okay, so this is a position versus time curve. All right, let's say calculate the average velocity between, let's say, t equals 0 and t equals maybe 3. Okay, so at t equals 0, the particle is here over here. Okay, and at t equals 3, the particle is over here. Okay, so average velocity is the slope of the line joining the 2 points. Okay, so it's going to be the slope of this line over here, or you can do it this way. Average velocity is x final minus x initial divided by t final minus t initial. Okay, so the initial point ti xi is this point over here, which is 0, 3. Okay, so this is 0, 3, and the final point, which is t final, x final is over here, which is its x is 3 and its x value is 0. Okay, so using these numbers, x final minus x initial is 0 minus 3, t final, which is this one, minus t initial is 3 minus 0. Okay, that'll give you negative 1 meters per second. Okay, so as you can see, it's negative because the line is inclined in this direction. If a line goes from this quadrant to this quadrant, the slope is positive, but if the line is inclined this way, it will be negative. All right. Number 2, calculate the displacement let's say between maybe t equals 2 and t equals 5. Okay, so we want to find the displacement between this point and this point over here. All right, so remember, we're looking for this one. Delta x is x final minus x initial, so we're just looking at the positions. Okay, so the x initial is over here, you see, which is 3. So we've got x initial is 3 and x final is over here. This is x final, which is negative 2. X final is negative 2, so the displacement is x final negative 2 minus x initial minus 3, which is negative 5 meters, which means the particle displaced to the left. Okay, it was displaced from here to this location, so it's displaced by 5 units to the left. Now let's calculate the instantaneous acceleration at, let's say, t equals 3 seconds, let's say. Okay, so we want to find instantaneous acceleration at this location over here. If you remember, instantaneous acceleration is obtained from a graph of position versus time at the slope of the line tangent to the curve. But if the curve is a straight line, then the tangent line is the line itself. Okay, so basically in this case, we calculate the slope of this line. Okay, so we can take these 2 points to get the slope of this line. Okay, so you can say instantaneous acceleration, in this case, equals average acceleration, because the graph is a straight line. Okay, so it'll be, I mean instantaneous velocity, I'm sorry, velocity, instantaneous velocity, we're talking the graph of position versus time. So instantaneous velocity at t equals 3 seconds. So we're looking at the instantaneous velocity at this point. The instantaneous velocity is obtained as the slope of this line, but for straight line, the tangent line is the line itself. So basically we have to calculate the slope of this line, that is horizontal change divided by vertical change. So in this case, the initial point ti xi, okay, this is our initial point over here, which is 2, 3, and then our final point for this line, if you take this line over here, is negative, the time is, well, let's say 3 is somewhere over here. Okay, maybe let's say it's 3.5. Okay, let's say the time is, or alternatively we can use these 2 points. It doesn't matter the slope of the line. So let's take these 2 points over here. So the initial point is, for this one, still 2 and 3, and the final point would be 3, 0. Okay, so we have t final, x final, the time is 3, and the position is 0. Okay, we're trying to calculate the slope of that line. All right, so in this case, the instantaneous velocity equals the average velocity because it's a straight line. So we have xf minus xi minus tf minus ti. Okay, so this is the final time, 0 minus 3, and the time is the final minus the initial 2. Okay, so you've got -3 or 1, that is -3 meters per second. All right. Okay. Number 4, let's say at what intervals of time is the particle at rest. The particle at rest. Okay, so we're looking the intervals for which the particle is not moving. Basically, we're looking for the points where the position is not changing. Okay, so you see, if you look at this interval, the position remains 3. The particle is at rest at x equals 3 over here, so it's not moving. So one of the intervals is from 0 to 2. Okay, the other interval is this one over here. It's not moving over here too. Let's say this time is 3.5 over here. Okay, so the intervals are from 0 to 2 and from 3.5 to 5. Okay, so we have from t equals 0 to t equals 2, from t equals 0 to t equals 2, and from t equals 3.5 to t equals 5. All right, so these are the 2 intervals where the particles are moving. But over here, you see the position is changing and it's moving to the left. All right. Next, we're going to look at the graph of velocity versus time. The graph of velocity versus time. Velocity versus time. Okay, so let's take a graph like this. So it's 1, 2, 3, maybe 4, 5, 1, 2, 3, -1, -2, -3. Okay, suppose this is a graph. It goes like this, and then it remains horizontal until t equals 4, and then comes back this way. Maybe it goes a little farther. Say 6, and then stops over here. Let's say this point over here is this is 6, this is 7, this is 8 over here, let's say. Okay, so let's ask some questions. A, what is the initial velocity? What is the initial velocity? Now remember, in this case, the graph is velocity versus time, okay? So velocity is the value of the vertical axis. So being asked for the velocity at t equals 0 is basically 0. The value velocity at this point is 0. So the initial velocity for this motion is 0. The particle is starting from the rest. Now let's say calculate the average acceleration, for the entire trip, okay? So that means starting from this point to this point over here, okay? So we're looking for average acceleration. Average acceleration is v final minus v initial divided by t final minus t initial. If you want to connect these 2 points over here, these are our points, this is our final point, so our initial point is the slope of the line connecting these 2 points over here, is the slope of this line over here. Okay, so you can simply calculate the slope of this line, or you can use this formula over here. Okay, so the ti bi, that is this point over here, because they're being asked for the entire trip, is 0 0. Time is 0, speed is 0, because 0 0 over here, and the final point over here, that is t final and v final. The time is 8, and the velocity is -1. Okay, so using this formula, vf minus vi is -1 minus 0, and tf minus ti is 8 minus 0. So you get -1 over 8 meters per second. Okay. Now let's calculate the instantaneous velocity at t equals 5. Instantaneous acceleration at t equals 5. Okay, so we're looking at the instantaneous acceleration at this point. Instantaneous velocity, I'm talking about acceleration, I'm sorry, instantaneous acceleration. Okay, so we're looking at the instantaneous acceleration at this point over here, and the instantaneous acceleration is the slope of the line tangent to the curve. Okay, but this is a straight line, so the tangent line is the line itself. All right, so basically it's going to be the slope of this line. In other words, the acceleration is a constant variable, so average and instantaneous are going to be the same. Okay, so we can take any 2 points in this line to calculate the instantaneous acceleration. The acceleration is a constant on this line because the graph is a straight line, so the average and the instantaneous are the same on this curve. Okay, so we can use any 2 points. Maybe we can use these 2 points over here to calculate the slope of this line. Okay, so in this case we have instantaneous acceleration equals a average, that is v final minus v initial divided by t final minus t initial. Okay, and the points are, if I take this point over here, it is 4 2. So let's say ti vi would be this point over here, which is 4 2, and then if I take tf v final, if I take my final point to be this point over here, that is 5 0. Okay, so using this formula, a equals vf minus vi divided by tf minus ti, we get v final is 0, v initial is 2, t final is 5, and t initial is 4. So you get -2 over 1 or -2 meters per second squared. All right. Now let's say, at what intervals of time is it accelerating? At what intervals of time is it accelerating? Remember, acceleration means an increase of velocity. So it's, you see on this interval the velocity is increasing, right? And on this interval it's decreasing. So it is accelerating on the interval 0 to 2. So the answer for this one is t equals 0 to t equals 2. Okay? At what interval is it decelerating? Remember, deceleration means decrease in velocity, so it's decreasing over here. So it'll be from t to 4, maybe t to, from t equals 4 to t equals 6. So this would be from t equals 4 to t equals 6. And at what interval of time is it not accelerating, or is it moving with a constant velocity? Is moving with a constant velocity, or with acceleration 0. Okay, so you see this is a velocity axis, so it's constant over here and over here. So it's from t equals 2 to t equals 4, and from 6 to 8. So this is from t equals 2 to t equals 4, and t equals 6 to t equals 8. Okay, these are the two intervals where the particle is not changing its velocity, where the acceleration is 0. In other words, the slope of this line is 0, so acceleration is 0, which means the velocity is not changing. The same thing over here, the slope horizontal line is 0, so acceleration is 0 over here, and the particle is not moving. Okay, now let's obtain displacement. Number 6, let's say calculate the displacement of the particle, let's say between t equals 0 and t equals 4. Okay, so we want to calculate the displacement from here to here. If you remember, displacement can be obtained from a graph of velocity versus time, as the area enclosed with the graph of velocity versus time and the time axis. So basically we have to calculate this area over here to get the displacement between t equals 0 and t equals 4. Okay, so we can divide this into two parts. So you can find the area of this one first, and then the area of this one, and then add them together. Okay, so I'm going to divide this into a triangle and a rectangle. So delta x, we can say, so delta x would be the area of the rectangle, the triangle. Now the base of this triangle over here is 2, and the height is 2. Okay, so we have 2 over here, and then plus the area of the rectangle. You see, for this rectangle the base is 2, from 2 to 4, and the height also 2. Okay, so we have 2 over here, 2 over here. Well, the picture is exaggerated, but they're both equal. So this is half of base times height, okay, for the triangle, 2 times 2, and then this is a triangle, 2 times 2. Okay, so you get 2 plus 4 6 meters will be the displacement in this interval. Okay, so displacement is obtained at the area enclosed between the velocity versus time curve and the time axis. So when t equals 0 and t equals 4, we're looking at this area. Okay, we can divide this area into the area of a triangle and the area of a rectangle. Okay, so this is base is 2, height is 2, so the area is going to be half of 2 times 2, which is 2. And then for this one you have base 2 and height 2, 2 times 2 is 4, 4 plus 2 is 6. Okay, now let's calculate the displacement between t equals 4 and 2 equals 8. Okay, number 7, calculate the displacement between t equals 4 and t equals 8. Okay, so we want to calculate this displacement over here from here to here. Okay, so you see, now remember, areas above the time axis are taken to be positive, so this is going to be positive, but areas below the t-axis are taken to be negative. The reason is, on this region above the t-axis, the velocity is positive. It means it's moving to the right, which makes positive. But on this range over here, the velocity is negative, which means it's moving to the left, and that gives you negative displacement. So the displacement is this area minus this area over here. Okay, so we divide it into 3 parts: this one, and this one. All right, so we're going to say, no, we're looking at this area over here, we're going from t equals 4 to t equals 8. Okay, so we're going to divide this into 3 rectangles. So we're going to say displacement equals the area of this rectangle first, this one over here. I'm going to write a triangle. This triangle, its base is 1. Diagram is exaggerated, but this is 1 from 4 to 5, and the height is 2. Okay, so you've got 2 over here. And then we're going to take the, now remember, now it's minus, it's below the time axis, and that is this rectangle over here. Okay, its base is 1, this one is 1, and its height is also 1 from here to here. Okay, 1. So we have 1 over here, and then we have the rectangle. We're also going to subtract that because it's below the t-axis, and that is a triangle of base 2. Okay, this is 8 over here, and height 1. So we've got this rectangle. Its height is 1. Its base is 2. Okay, so the displacement is, this one is above the t-axis, and that is half of 2 times 2. Okay, that is the area of this times 1, I'm sorry. This is, its height is 1. Its base is 1, so it'll be times 1 over here. Okay, and then minus the area of this, which is half 1 times 1, minus the area of this one, which is 1 times 2. Okay, so we have 1 over here minus half minus 2. Okay, so that's half, this is half, minus 2 is negative 3 over 2. So you see, the displacement is negative 3 over 2, or negative 1.5 meters, which means displacement to the left. So remember, when calculating displacement, the displacement above the t-axis, this area over here, is saying positive because the velocity is positive over here. It means the particle is moving to the right. That makes the displacement positive. But below the t-axis, the velocity is negative, which means the particle is moving to the left, which makes the displacement negative. So areas below the t-axis should be negative, and areas above the t-axis should be positive.